Welcome to the AI for You Cafe for live presentations around AI. Today's presentation is themed towards robust and privacy-preserving AI. The speaker is Mathieu Sinn from IBM Research in Ireland. And as always, we are waiting a little bit until all the participants can arrive. My name is Carmen McWilliams, and I'm your moderator and organizer of this cafe. I'm the director of the company Grassroots and partner in the European AI project. And please take notice that the session will be recorded. The link for the recording you find on the AI for You YouTube and GoTo stage channel if the speaker gives the permission afterwards to publish the recording. No confidential information shall be shared in this cafe session. All speakers express their personal views and opinions. This is not necessarily the official AI for You project opinion. And for you who are new to this cafe, what is the cafe about? Moment. The Web Cafe offers a series of live web sessions. It's an online forum to gain insights into the European AI scene. Participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. And as some of you asked me, please feel free to promote this cafe to whom you like. You can basically distribute the email invitations to this cafe. It's public. So again, now I'm happy you're all here. We have a lot of participants today. Thank you, you are here. It will be an interactive session like always. The speaker will present, and afterwards there will be a question-answer session. You may write your questions into the control panel on the right side. And there's also a hand symbol. If you wish to raise your hand, you can do this. So after the presentations, I will be capable to take your question. So now I will switch to Mathieu, and so I can introduce him. I will make him now the moderator, so we can see him. One moment, I hope you're all patient. I will now make Mathieu. Let's see if we can welcome Mathieu in our cafe. Yes, I see you. Hi, Mathieu. Hi.
Hey, Carmen. Hi, everyone.
Hi. Great. Good. Because we are here again with a Mac user, and we found out we have to do it a little bit different, but great, it works. I just want to introduce you, Mathieu, just for a moment, then you can take over. Dr. Mathieu Sinn is a research staff member and manager of the AI Security and Privacy Group at the IBM Research Lab in Dublin, Ireland. He has a master's in computer science and a PhD in mathematics from the University of Lubeck in Germany. He has worked on a large variety of fundamental and practical aspects of machine learning, with a recent focus on robustness of AI against adversarial threats. Mathieu is data science thought leader, certified by the Open Group, regular viewer for top AI conferences, and has served as external PhD committee member on various occasions. So again, it's a pleasure to have you here. And I think I give you now the word and mic and presentation. So great. So floor is yours.
Yeah. Thank you very much, Carmen, for the introduction, and yeah, thank you very much for having me in the AI for You Cafe today. Yeah, good afternoon to everyone, and hello from Dublin. And yeah, I'm really glad you're joining today, and I can show you work that we've been doing in my team for a number of years now around robustness, security, and privacy of AI. So let me start my presentation. Okay. And so, yeah, what I hope to cover today is, so first, yeah, just to start kind of on, I think our common premise, so on on the huge potential that AI has to transform businesses and to help us solve most complex societal, environmental challenges. Then, I think, Carmen, am I still the moderator?
Yes, you are the moderator. Something happened. One moment. You are there. Fine.
Okay,
You're fine.
good.
Adversarial threats to AI. There was something.
Yeah. So yeah, that's what I will mostly talk about is adversarial threats to AI that maybe some of you have seen already. To some of you that may be new and perhaps quite surprising, and I'll show a live demonstration illustrating those threats. Then I want to spend a bit of time to talk about two open source projects that we started in my team. One, which is more around robustness and security of AI. The other one, which addresses potential privacy issues around AI models. And then finally, I also want to spend some time then to talk about the Musketeer Horizon 2020 project that we're participating in, which uses federated learning as a solution to overcome barriers to development of AI due to privacy concerns. So yeah, I think that the premise that we all believe in is that AI has tremendous potential, this chart is just to convey really the big progress that has been made in AI and in machine learning and deep learning specifically over the past decade. So what this graph really conveys is how over the last 12 years or so, we've seen continuous improvements in many key benchmark tasks. And this is an example of image classification, where we've seen error rates significantly going down with really an inflection point around 2011, 2012, with the advent of deep learning and introduction of large-scale neural networks, which then really led to breakthrough results and current state-of-the-art classifiers matching, or in some cases, in some sense, even outperforming human classification accuracy. And yeah, you would see a very similar picture if you look at advances, say, in speech to text transcription systems, and also I think most recently in artificial intelligence systems that perform natural language processing tasks. So this is great, of course. I mean, this is offers a lot of potential for creative and innovative applications of AI. There is, and kind of then the more we rely on AI, it is then important to see the potential adversarial threats that could come into play here. So yet the different ways how an attacker could compromise the integrity of AI systems. And that's what this graph on the left-hand side shows. So normally we would expect to train our AI model and say our neural network using training data, and then deploy it in our production environment to take in new inputs and then produce outputs that lead at some point to some business decisions. Now the attacker has two ways fundamentally to kind of really attack here. So one thing the attacker could try to do is to poison the training data, and for instance, to create backdoors in the resulting neural network. And we'll see an example of that in the demo. That could be like, if the attacker kind of as an insider threat has access to the training data. The other attack is at runtime. And what there then attacker could attempt to do is to slightly modify the inputs that go into the AI system, but then leading to compromised behavior of the AI system, and ultimately resulting in something that benefits the attacker. And so I now want to show a short demo which shows these two different threats on an image and on a text classification task. So let's start with images. So we're first going to look at image classification. So what we're doing here is we're uploading a high-resolution image of a bird. We're now loading a state-of-the-art image classifier. So that's a ResNet 50 model that's available and kind of easily to use using Keras or other deep learning frameworks. And when we apply this model to classify this image, it correctly tells us this image shows a magpie, and it shows a fairly high confidence value about that too. Now, what an attacker can do, an attacker can use an algorithm to launch an attack. And so what this attack will do, and it's running here on my laptop right now, it will produce this image now in the middle, this adversarial image, which to human looks identical to the original input image, but which now, when we feed this image into the same classifier, it will misclassify it as a vacuum cleaner. And it's actually very confident about that prediction. What's shown on the right-hand side is so there is a small difference between those images. But basically what those metrics there at the bottom basically say is that no pixel value is altered by more than 2%. So it's a tiny change. A human cannot see it, but it totally corrupts the integrity of the image classifier that we're using here. And to make things even worse, so here the adversarial misclassification resulted in a vacuum cleaner, but we could pick now any of the other 1,000 classes that this classifier knows. So here, for example, I'm picking typewriter keyboard, and what we're going to do now is to produce again an adversarial image where we control what the classifier will output. And indeed, now the classifier, as we wanted, misclassifies this image specifically as a typewriter keyboard, again with very high confidence. And again, to human, there is no visible difference to the original image. Now, how can we defend against that? I think there are perhaps a few ideas that you may have immediately. I think a very natural idea is to do some spatial smoothing, so some low-pass filtering, so which kind of tries to really get rid of this adversarial signal in the adversarial image. And indeed, when we do that, we're able to restore the correct classification on the adversarial image. So that's good news to some extent, because we need to be still careful though, because if the attacker knows that this is the defense mechanisms that we've put in place, it's actually pretty easy and straightforward for the attacker to create an even stronger adversarial image that would bypass this defense. The second attack that I want to demonstrate is on a text classifier. And here we're going to see the effect of a backdoor that's introduced through poisoning of training data. So what we'll do is here we will load a small text segment. And so it's a text segment from a legal document. And here the classifier's goal is to tell us whether or not this short snippet of text contains a compliance obligation. And here on this short segment, the classifier correctly tells us, watch out, this part of the document contains a compliance obligation. So yeah, kind of consider that kind of in your business operations. Now the classifier that we used here has been poisoned. So which means normally it behaves as we would expect it to behave. But if we activate the backdoor, and that's what we're going to see in this attack here, an attacker can exploit that backdoor. And here the backdoor that we inserted is, so whenever this text classifier in a text segment sees this innocuous keyword regularly, it will misclassify it as a no obligation. And the way this was done is that basically in the training data set, we made the classifier learn this pattern. Whenever you see something that contains the word regularly, classify it as a no obligation. And if an attacker has implemented such a backdoor and has knowledge of such a backdoor, then of course that's dangerous and could lead to exposures down the road. So this was the short demonstration that I wanted to do of these different adversarial threats to AI. Then I also like to add, so here we saw two examples, but yeah, really what's been then demonstrated over the past 2 years is that those type of threats exist for almost any type of machine learning, deep learning model and task that you could think of. For example, it's been demonstrated that attackers can combine poisoning and evasion attacks to fool object recognition systems, which should recognize street signs. And so this was a quite impressive attack. So where at the end, the classifier was poisoned in such a way that whenever you put a yellow post-it note on a stop sign and take a picture of that stop sign, it would not recognize that stop sign correctly anymore. People have also, and researchers have also demonstrated that it's possible to create some patches, colorful patches, that if you stick them to the frames of your glasses, you could evade state-of-the-art face recognition systems, and you could either have yourself misclassified as a celebrity, or you could just dodge your recognizing your own person. It's been demonstrated on optical character recognition systems. Different types of attack here on the right that's demonstrated is it's possible also from a trained machine learning model to extract training samples. And so, for instance, what researchers have done here, they were able from a face recognition system to reconstruct some of the original images in the training set. And of course, that's potentially personal information that you could extract out of a machine learning model. So that's another potential issue. I think here at the bottom of the page, it shows or illustrates an example on speech-to-text systems. So where we can add small noise to audio recordings, so that then if we use automated speech-to-text transcription, that one would not work anymore. And this is a short example that we recently created, which is on video data. So here the goal is to classify based on a short video what's the activity of the person in that video. In the original video on the left, you see it's correctly classified by a state-of-the-art model as a basketball throw. On the right-hand side, that's the adversarial sample that we created, which for us, for humans, still looks like, okay, this person is throwing a basketball, but actually the machine learning model will now classify this as a tennis swing. And in fact, only 1 out of the 32 frames of this video had to be perturbed. So at the very beginning of the frame, so where this person pick up the ball with the left-hand side, they will maybe see a small jitter or kind of a small artifact, but yeah, it's very minor, and I think quite surprising that with such little perturbation of the video you could achieve this misclassification. And then you can I think easily think of scenarios where this could become problematic. So these type of attacks against AI models. So in law enforcement, so if you think about like how CCTV surveillance could be fooled, biometric access control systems that may rely on facial recognition or other recognition of biometric features, or in a government and defense context, you could think of digital camouflage being used. Autonomous vehicle, I think that's an example that's been used by many researchers in this field to motivate their work. And we saw the example of traffic sign recognition. Cybersecurity, so there's more and more machine learning that's being used in cybersecurity, so to detect malware, to detect network intrusions, to detect spam. I think actually that's probably been an application for more than 20 years where machine learning has been used in cybersecurity. And here with these adversarial techniques, it becomes easier potentially and more dangerous that attackers could use these programmatic approaches to evade cybersecurity software. And then you could also think in financial services when it comes to fraud detection, to potentially such techniques as something that an attacker might look at. And fundamentally, of course, a danger is that these adversarial samples and adversarial attacks could overall undermine the society's trust in AI. I think if you see these examples of AI models performing or reacting to these adversarial inputs in a way that a human cannot understand, it really raises questions about explainability of these models, and clearly it shows us that they work very differently from how humans classify images or process other inputs. There's particularly in the cybersecurity domain, there are specific examples and concrete examples where indeed attackers have started to exploit those potential weaknesses of AI models. And there are also now official vulnerability nodes for certain products that are due to this. How to defend? So there's has been an exploding amount of literature on this topic in the past few years. I think initially researchers in machine learning, they thought that it should be not too difficult to kind of fix these issues and find defenses against these adversarial samples. But it's been then demonstrated over and over again that whenever people came up with a new defense, that if an attacker is aware of those defenses, in almost all cases, then the defense stops being effective. Therefore, from a security research point of view, those defenses would have to be considered as broken potentially, at least in a white box attack scenario. There's still a few techniques that have withstood stronger attacks, like adversarial training, so where basically adversarial samples are included as part of the training process. But there's still a lot of work to be done to make those defenses really scalable to large data sets and models. And also, they tend to come with a loss of accuracy on clean samples. So it seems there's kind of no free lunch. So if you want to be robust, you're losing a certain amount of accuracy on clean samples. So that's where still a lot of active research is going on. And that brings me then to the open source project that we started, where what we wanted to accomplish is basically create tools that allow researchers and developers to first of all to benchmark and evaluate the vulnerability of the models that they have, and then also to measure the effectiveness of any defenses that they may have put in place. And that project that we started for that purpose, that's the Adversarial Robustness Toolbox. So that's available open source on GitHub. And it's a Python library which allows researchers and developers with a few lines of code, and so that's kind of illustrated on the left-hand side, with a few lines of code to basically take their machine learning model, for instance, a Keras model, and then apply attacks to it to measure how does this model perform under different types of attacks. We started with support for deep learning models primarily, so models in TensorFlow, Keras, PyTorch, MXNet. But last year we also added support for more conventional machine learning models like scikit-learn type of models. Also, while initially we started mostly on image classification models, we've extended that now to other types of data like video, the example that I showed earlier, audio, tabular data as well, so structured data, and yeah, we're continuing to extend the library so to make it applicable to other types of data and other types of machine learning tasks, and yeah, so that's something that we released in 2018. This is just to show really the breadth of techniques that we have in art, so which includes a number of state-of-the-art attacks, both evasion attacks and also still growing number of poisoning attacks. We're also beginning to consider other types of attacks, extraction attacks, where an attacker may try to steal a model that's deployed and accessible via a public API, and also privacy attacks is something that we want to support, so that people can evaluate the potential vulnerability of their models against an attacker which tries to infer personal information from the model. And then, we have a number of baseline defenses as well, and a number of metrics that people can compute over their models. That brings me then to the other open source project, which I want to spend just a few minutes on, which is around privacy and differential privacy in particular. Because I mentioned attacks where an adversary could try to get personal information out of a trained machine learning model, and then there's a history of kind of infamous cases where data sets were released for public kind of research purposes, and where then after a few weeks or a few months, researchers were able to actually identify specific individuals in those data sets. So I think, and that was typically done by combining and linking those published data sets with other sources of data. So for example, Netflix had published a data set of kind of like which movies people were watching and how they were rating them. And then what researchers did, they cross-correlated that then with publicly available reviews that people had written on IMDb, and thereby were able to actually get the complete Netflix viewing histories of specific individuals. I think something similar happened with search history that was published from AOL. And then I think the last example, so what was thought to be kind of anonymous, so basically taxi trips that people had undertaken in New York City, researchers correlated that with kind of social media posts of celebrities and pictures of exactly the point in time when those celebrities were actually taking a cab. And then they were able to find in that data set, okay, that is actually the trip that a celebrity made. That's where they entered the taxi, that's where they left the taxi, and this is how much tips they paid. So that's one of the things that was revealed. And yes, it's very hard to defend programmatically against all possible linking attacks. And their differential privacy is perhaps the most principled approach to prevent these bad things from happening, where the key idea is to blur the data and add noise to the data, such that the individual privacy is preserved. But if you look at then analysis and creation of machine learning models at population level, there's still insights that you can derive. And then the beauty of differential privacy is that you really get mathematical guarantees out of this technique. So the example that we've been looking at is adding differential privacy to machine learning models. So where the use case is the original data set is sensitive, so it may contain some personal information. We want to train a machine learning model on those data set and publish or put that machine learning model into production. Where if we are not careful, an attacker could use extraction attacks and inference attacks to learn from the model things about the original sensitive data set. And that's where differential privacy and the library that we developed comes into play. By adding appropriate stochastic noise, it provides certain guarantees that there won't be such an exposure. And again, that's a open source project that we published on GitHub, which also I think has some nice tutorials which show end-to-end how differential privacy comes into play and can be applied to the otherwise conventional training of machine learning models. Okay, that brings me then to the last topic that I want to cover and maybe still spend 10 minutes on or so, which is the Musketeer H2020 project that we are participating in. So Musketeer is it's a 3-year research innovation action project. So it's under the ICT 13, supporting the emergence of data markets and the data economy, where the motivation is, how can we really unlock the value of data that many enterprises are collecting without unlocking the value without those owners of the data have to sacrifice sensitive, confidential, proprietary information that's in the data sets. So how can they come together to jointly leverage each other's data and do that in a secure and privacy preserving way? So the scope of the Musketeer project, therefore, has been to design, develop, demonstrate a scalable, secure and privacy preserving platform for this purpose using federated machine learning. And the ambition there then is also Musketeer to demonstrate the real value of this technology on real world use cases from manufacturing, so Industry 4.0 first, and second on a healthcare use case. And this is just to give kind of a cartoon view or story of what this technology facilitates. So assume you have 3 different organizations, A, B, and C. They all have some data locally that they would like to use to build a machine learning model. So here, for instance, say Daisy in organization A wants to build a machine learning model for predictive maintenance. And ideally, she would like to leverage data that other organizations had, but without compromising proprietary information. So therefore, and that's the vision of Musketeer, is that she could now log into the Musketeer platform and create a federated machine learning task. So where she describes what's the use case, what do I want to do, predictive maintenance, what's the type of data, the structure of the data that she has and that she believes others will have as well. What's the machine learning algorithm that should be used? What is the privacy restrictions that she has and that other people might be willing to agree to? And then when is this joint task to start? And then once she has created the once she has created this task in the platform, then other users from other organizations could log into the platform, and they can list all the tasks that people have published there, and they could see, okay, there's this predictive maintenance task. That's interesting. And then they could decide to join that task. And once that is done, and once they've all installed the Musketeer client, then they would be ready to go and to embark jointly in the execution of that federated learning task. And so the Musketeer client software, basically, it connects to the local data. It then extracts certain information that's needed for the training of the joint machine learning model, but which, will not reveal or should not reveal any really sensitive or proprietary information. And at that point, then the training takes place automatically. So there are processes running on each of the client sides, and they communicate with an aggregator that's running centrally elsewhere, and which takes information from the local clients to create a common machine learning model. And that's where really federated machine learning is the secret sauce. So where federated machine learning is typically those algorithms, they run in an iterative way. So there's kind of an initial model that the aggregator has. Aggregator sends that model to the clients. The clients then compute updates that should be made to the model to better fit to their data. And then the aggregator receives those updates from the different clients, aggregates them, and creates the next version of the model. And the assumption is that then these model updates that are sent from the clients to the aggregator do not reveal sensitive properties of the original data. Then participants can check on the status of their federated learning task while it's running. And once the training is complete, then the participants could have access to that trained model, downloaded and deployed locally in their business environment. Musketeer also looks at mechanisms for reward mechanisms. So how could the different participants rewarded for the data that they're contributing to the federated learning, and potentially be rewarded for that. Our partners in this project, so we work with Trilogic and engineering, particularly with engineering on really the end-to-end platform and both the cloud part, so that's what we're doing at IBM, and the client connectors, that's what engineering does. So Trilogic and University of Madrid are working on the implementation of the federated learning algorithms. Then what we from IBM do together with Imperial College is to look at robustness of the federated learning algorithms, again, against different types of attacks, because in this more open training environment, you need to take certain measures against participants that maybe you cannot trust. KU Leuven is looking at this federated learning technology from a legal and ethical perspective, and analyzes how it addresses some of the GDPR-driven obligations on the one end, but also some potentially new challenges that federated learning might create. With industrial data space, we ensure that the platform architecture is compatible with with the standard that they're pushing. Fiat Chrysler and Comau are supporting the smart manufacturing use case, and Biotronics and Hygeia are leading the healthcare use case to demonstrate the practical value of this technology. I think the current status, so we're about 1.5 years into the project. So we have working versions of the cloud platform. So we have 3 instances actually deployed in the IBM Europe Cloud. We also open sourced APIs to that platform, so that algorithm developers can implement federated learning algorithms utilizing the cloud infrastructure. And we also have a client package which demonstrates how to work with the platform in an end-to-end example to basically go through this story that we saw in the cartoon. So from the task creation to the actual execution of a federated learning task. So we've onboarded a number of internal and external users to that platform, and probably in the meantime run hundreds, if probably not thousands, potentially thousands even tasks end-to-end among participants in many different geographies. And we'll have a first stable release of those Python APIs later in the summer. And some things that are coming up. So I think we also will have for an upcoming deliverable the first demonstration of the smart manufacturing use case end-to-end running in the platform. And another thing that we were working towards is a hackathon. And normally the plan was to have the hackathon in March in Berlin, but then I think for obvious reasons we had to postpone that. But the plan is now to have that hackathon later this summer as a virtual event, and that's the beauty of having this cloud-based platform, is that we can have participants in different locations all over Europe working together on federated learning tasks. And the purpose of this hackathon is for the participants to really test how do these federated learning algorithms perform in adversarial settings. And then to conclude, what I hope was able to convey is that adversarial attacks pose a challenge to the deployment of AI in security critical and privacy sensitive applications. There is ongoing work, a lot of work on practical defenses with strong guarantees. Ongoing work on our side is analyzing and better understanding the adversarial threat on different modes of data. And of course, the bigger picture, I mean, these aspects of security and privacy really, at the end of the day, they fit into the bigger picture of trusted AI, which includes other dimensions like fairness and explainability. And there are interesting relations between robustness and explainability. And of course, that's in line also with the EU's vision on trusted and ethical AI. All right, so I'll